We are gonna look at quadratic modeling today. So what is even that? So let me just show you what's going on here. So what happens usually in real life is you don't get perfect points. Like you see these points are perfectly aligned so that you can fit a curve through it. But it doesn't really happen in real life. What you get is something like this, where the points are a little bit randomly scattered and depends on what function you want to fit into this. You see how the line doesn't really touch all the points? Yeah, it's because this is simply a model, okay? And what we do with a model is we use it to predict future numbers. So for example, let's say this is our model. Let's say it's x squared plus 3 or minus x squared plus 3. And let's say y is the sales and x is the number of items, yeah? So using, let's say for the data, using the data from 2022, we came up with this model. And what you can do is you can make predictions about the future. Now in 2023, let's say this is 2022, 2023, we can predict what the sale amount will be, okay? So it's basically used to predict future numbers. And let's look at a question here. So here they've given us some data points. First thing you want to do every single time when you're trying to fit a curve is to graph it. Graph the coordinates. So our first point is 0, 0. Second point, again, how far is this going? Let's say 10, 20, 30, 60, 90. And our first point is 22. Let's say this is 22. Next point is 60 and 30. Let's say this is 30. Next point is 80 and 27. And the last point is 90 and 22.5. So that's a rough sketch. Yeah, usually you do this using technology, but if you want, you can also do it by hand. So let me show you how that works. So let's say that's our points. What you do is you connect all the points using a curve, and then you just follow it down along, okay? Let's say this point, I know they used a graphing calculator here. That point is 120. So this point is 0, 0. It starts at the origin, and that point over there is 120. The question is, what's the equation of this curve? Which form should we use, the factored form or the vertex form? We have these 3 points. Look at this. You can use either of the form because you have the vertex and you also have the x-intercepts, yeah? Remember that? The x-intercept was a x minus s, x minus t. This is the factored form that uses the x-intercept, and you want to use this if you have the x-intercepts, or if you have the vertex, which we do have here, you can use this form, where h and k is the vertex, yeah? So if you want to use the factored form, again, what are our x-intercepts here?
0 and 120.
Yeah, so let's just replace s with 0. So x minus 0 is still x, and x minus 120. How do we come up with what a is? Look for any other point on the curve.
The vertex.
Yeah, the vertex. If you were to plug y as 30 and x as 60, that should give you the a value. So this is a times 60 times negative 60 is a negative 3600, 30. So a is going to be 3 over negative 360 or 1 over negative 120. That's our a value. Plug that over here, and that's the equation of the curve, okay? So that's how you would do this. If you want to do this using technology, it might be a little bit different. Okay, let me just show you how this is done. So what are our points? So I'm just gonna type in the points here. So it is 0 on the x, 30 on the x, 60 on the x, 80 on the x, 90 on the x. And then on the y, we have 0, 22, 30, 27, 22.5. When would you do this? I don't know, maybe for a project or a summative or something. Then what you want to do is fit a curve, okay? Highlight your points, scatter diagram, you see that? Then you'll get a curve. And how do you fit it? What you do is you go to something called trend line. Trend line is fitting a curve. Go to a trend line. Now, we don't want a linear. We know this is not linear. We know this is quadratic. Yeah, quadratic means it's a polynomial. Look at that. Order 2. Order 2 means it's a quadratic polynomial. You can try and fit an order 3 or order 4, but we know this is a quadratic, so we're going to stick with order 2. And then finally, you can get the equation by clicking display equation. And that's the equation right there. Now, is that the same thing as what we got? Let's see. So this is what we have. Where did it go? So let's double check. Again, we have the right answer. I just want to show you the difference between using technology and using by hand. So our equation was y equals 1 over negative 120 x and x minus 120. Yeah, you see that?
Mhm.
So now let's open the brackets. X times x is x squared. X times negative 120 is, well, negative 120x. And then we have 1 over negative 120. Now, what is 1 over negative 120? It's going to be a very small number. 1 divided by negative 120 is actually 0.00833x squared plus 1x. So this is what I got after I opened the bracket. Now compare this with this. Again, there's a negative sign. The y-intercept, you see this? The y-intercept is negative 0.09. It's almost 0, 0. Yeah? It's very, very close to the origin. And for the x, they got, or technology got 0.99. We got 1. For the a value, technology and we both have the almost exact same numbers. So that's how you can use Excel to fit a curve. And it's usually done with Excel, at least on this level. If you have a lot of points, Excel doesn't really work. Excel only works till 60,000 points. But let's say you have more points than that, then Excel fails. You need to use something else. You need to actually use coding after the data gets certainly big. You need to use what's the software that you can use? You can use something called R to fit more than 60,000 points. But Excel is good for like high school level. Excel is perfect. All right, let's do another one. Maybe this time will be a little bit more precise. Same idea. They've given us a table of values and they have asked us to come up with an equation. What's the first step? Just graph it, yeah? Straight
Mhm.
up take the coordinates, graph it out, see if you, and which form of the quadratic you can use. This is going to be super annoying to graph because of the decimal points. So this is just going to be an estimate. So 2, 4, 6, 8, 10. So our first point, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our first point is 0 and 10. Well, that's a pretty easy point. Our next point is 0.3 and 9.56. That is a super annoying point. So 0.3 is going to be somewhere to the left of 0.5. And 9.56, this is 9, so 9.56 is going to be somewhere there. Next point is 0.6 and 8.24. So maybe right there. 0.9 and 6.3. 1.2 and 2.94. 2.94 is a little bit under 3. And then the last point is 1.5 and negative. I don't know why I went so far into the x-axis. There's only 0 to 2. So 1.5 and negative 1. So maybe somewhere there. And now this is what we have. Alrighty. How do you come up with an equation for this? Which form would be helpful here? What's happened here is that there is a diver. He starts from up here, right? He starts from the tallest point, and then he dives into the water. And we're trying to model this curve using a quadratic equation. Do we have the x-intercepts? Like, do we know what that point is there? See this?
Mm-hmm.
Yeah, we can estimate that, but we don't know what the other x-intercept is, okay? To use the factored form, you need both the x-intercepts. So maybe the factored form approach is not the best here because you need both s and t, or x1 and x2. Maybe the vertex form would be the best because we know that point is going to be the tallest point. So, and again, he's handstand dive, so it's not like he's leaping off the thing, yeah? He's not leaping
Mm-hmm.
off the platform. That means that's going to be our tallest point. That's our vertex. So we need to use this form. A x minus h squared plus k. What's h and what's k? It's the tallest point. It's the vertex. What's that for us? Look at the curve. Tallest point is always the vertex, right? This right here. That is our tallest point. That's our vertex. Because the way this quadratic will eventually look is it's missing a second half. There's another chunk to it, which we don't know what that is, but there's another chunk to it. It's a curve, right? So it needs to have both sides of the curve. So what's our vertex? What is this point?
0, 10.
0, 10. So put y as 10, put x as 0. So not x, not y. That's our h comma k, okay? This is our h comma k. So put h as 0, so x minus 0 squared is just x squared, plus k is 10. How do we find the a value? You just need another point on the curve. Any other point would work. You can just plug in any of these points, you see?
Mm-hmm.
You can plug in any of them. Which one would be the easiest? It honestly doesn't matter. So I'm going to plug this one because this is fairly close to 1. So y is going to be 6.03. A we don't know, but we know x is 0.9 squared plus 10. How do you solve this equation for a?
You subtract 10.
Yeah, and then?
You square root.
No. Try again. So I subtracted 10. I got negative 3.97. A times 0.9 squared is 0.81. Divide by 0.9 squared, okay? You would square root both sides
Mm-hmm.
if you had a squared equals something. If the variable has a square on it, then you would square root. Here you simply divide both sides by 0.81. Divided by 0.81. So that gives me an a value of negative 4.9. So our equation is negative 4.9 x squared plus 10. That is our equation. Now we're going to verify this. You can open a new sheet here. You see down there, sheets? So this, you can even rename it. This can be like, you usually do this like if you're doing like a project or something, you just want to stay organized. So you're gonna go down here, it's gonna be like question 2, right? Now, what are the data points for question 2? So we have 0, 0 0.3, 0 0.6, 0 0.9, 1.2, 1.5. You can also do this on Desmos, but it's easier on Excel. It's quicker. 2.94, negative 1.03. Right. Step 1, plug in the points. It's very simple. Step 2, highlight your points. Go to charts or insert charts. This one, scatter plot. Scatter plot, and then right click on the points, trend line is your curve of best fit. And again, we're sticking with polynomial degree 2 because it's a quadratic, not a linear. Linear would work here actually, but we know quadratic fits better. So let's go to polynomial, boom, and then you just wanna show your equation. And we're gonna compare this with what we have. So it's a good estimate. You see, like the A values are almost the same, yeah?
Mm-hmm.
And the intercept is the same. The only difference is we don't have this, but look at this. Look at how small this is, 0.0058. This is not gonna make a big difference or a big dent, okay? It's almost insignificant, this 0.0058. So we're pretty close. So that's how you do it by hand. And you can always verify it using technology. This one, can we graph this precisely? So on the x-axis, we go till 4. And on the y-axis, we go till 20 actually. Do I have 20 lines? Let's see. I'm gonna need some space. I don't know if I have 20 lines. Maybe I'll go by 2. Yeah. So on the x-axis, it's easy because you're only going to 4. So let me just go 2 at a time now. 1, 2, 3, 4. On the y-axis, we need to go till 20. I don't know if I have 20 lines, so I'm gonna go 2 things at a time, 2 units at a time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And now we're gonna start plotting. The first point is 0, 0. Notice, whenever you're doing this, notice what they've given you. They've given us both the x-intercepts because we know 0, 0. We also know 4, 0, right? If they have given us the x-intercept, which form of the quadratic is best?
Factored.
Factored form, because we have the x-intercepts. Now the next point is 116. 16 was here, so 116 is there. 220. Now that's going to be our vertex. We can always use the vertex form as well because that's the tallest point on the curve. Next one is 315.5. That's going to be annoying. 14, 15 is here. 15.5 will be in the middle between this and this. So 3 and 15.5. And that's our last point. Now we're just going to connect the dots. Easy peasy. All right, if you want to use the quadratic factored form, y equals a, x minus s, x minus t. What's s and t for us here? Remember, they are the x-intercepts.
0 and 4.
0 and 4. So you have x minus 0, which is just x, and then you have x minus 4. How do we find the a value?
You plug in another point.
Yeah, you plug in another point. I'm going to plug in the vertex because that's a beautiful point, 220. So 20, a we don't know, x is 2, x is 2 again. So you have a times 2 times negative 2, that's a times negative 4 equals 20. So that becomes a becomes 20 divided by negative 4, a is negative 5. Therefore, our equation is negative 5 times x minus 4. So this is the answer to part A. Part B, use the equation you determined to find the height after 0.5 seconds. So is x 0.5 or is y 0.5?
X is 0.5.
Yeah, x is 0.5. X is always time. Remember, time is always going to be the independent variable. Nothing beats time. So 0.5, so negative 5 times 0.5 times 0.5 minus 4. Like that. Plug that in a calculator. Negative 5 times 0.5 times 0.5 minus 4. I get 8.75 meters. What does that mean? That means when the time is 0.5. You see here? Our model gives us a y value of 8.75, and that's what prediction means. You can use these 5 dots or data points that they've given you, and you can make predictions about the missing values. Like we can find out what's the height when the time is like 1.8 seconds or like 3.6 seconds. Okay, this is called prediction. When you're doing this, you need to be very careful because you might fall into a trap. I'm going to ask you a question. Is this model, what if I asked you, what's the height at 5 seconds? Would this model still be valid?
No.
Why not? What's wrong at 5? Or what's wrong after 4 seconds?
The height would be negative.
Yeah, but this could be a water diving question or something, right? No, it's not because the height is negative. It's because there's a flaw in the model after 4 seconds. And this is something you have to be very concerned with, very careful about, okay? This one. You cannot make predictions, okay? You cannot make predictions beyond the data values that you have. So what that means is even if, let's say, this curve looked something like this, okay, let's say there's no restriction on the height. It made something like this. This data value is at 1 second. This data value is at 4 seconds. You can only make predictions, okay? You can only make predictions for between 1 and 4 seconds, like here. You cannot make predictions at 0.5 seconds because the model that we have didn't include 0.5 seconds, or the minimum x value was 1. You see this? The maximum y value is 4. Beyond this, what happens, that the flaw is that it may not be a quadratic. Look at this. After 4 seconds, right, we don't have the data points. That's why we can't make predictions, because it may not be a quadratic. It may be a linear, and our quadratic fails, or it could be like a sine curve or something, right? It's the unknown region here. So you cannot make predictions beyond the minimum and the maximum x values, okay? Because we don't know. It may not be the same model. It could be, but there's a high chance that it also could not be. So do not make predictions beyond the data points that they've given you. That makes sense?
Uh-huh.
It's not a difficult concept. It's just graph it. Like you see here, we cannot make predictions beyond 0 and 8. Okay? 0 on the x and 8 on the x. We cannot make predictions beyond this. And the idea is the same. Every single time they give you coordinates, plot it and come up with an equation. All right, now I'm going to look for my scale. So on the x, we go from -4 to 2. So that's not going to work. I need the negative. I need quadrant 2 as well. So maybe something like this. And on the x, we go from, this is annoying, we go from -8 to +10. All right, not a problem. So let's start plotting it. So -4 and 10. I'm gonna go up by 2 units. 1, 2, 3, 4, 5. So that's 10. -4. 1, 2, 3, 4 is -4. That's our first data point. The next one is -3 and 0, which means it's down here. The next one is -2, -6. So -2, -4, -6, and -2. That's our third point. How many do we have? 6 points. The next one is -1 and -8. So that's gonna be down here. Next one is 0 and -6. 1 and 0, and 2 and 10. So there you go. That's our curve. I'm just straight up plotting the coordinates. Nothing tricky about this so far. And then you just want to connect the dots, and we are done with the graph. So you can see we have both the x-intercepts and we also have the vertex. This point is 1, 0, so that's our first x-intercept. That point was -3, 0, that's our another x-intercept. And our vertex, which we also have, is -1 and -8. So there we go. We can use either approach. It says factored form, so we need to use well, if it didn't say factored form, you can do both, but here we're kind of restricted. So again, factored form, x minus s, x minus t. What's s and t? Remember, it's the x-intercepts,
3 and 1.
a -3 and 1. So plug s as -3 becomes +3. Plug t as 1 becomes x minus 1, like that. How do we find y?
You plug in another point.
Yeah, you plug in another point, and usually vertex, if you have it, would give you the best model. So y is -8 when the x is -1, like this. So you get a times 2 times -2 equals -8. So you can a times -4 is -8. A is +2. So our equation, does it make sense that the a value is positive here? Should the a value be positive? Yes or no? It's opening up.
It should be.
It should be, so it makes sense. Yeah, you can verify if you've done it kind of right. If we got a negative a value, that means we know our model, something's wrong with it. All right, that's the answer to part A. Part B, express your equation in standard form. Standard form just means you open the bracket. It's going to look something like this, which is what the Excel spits out. It always spits out the equation, if you've noticed, in standard form, not in vertex form or factored form. So how do you go from a factored form to a standard form? Simply open the brackets. That's all you have to do. You FOIL it. So you're going to go x with x, x with -1. What's x times x?
X squared.
So yeah, you get x squared, x times -1 is -x, and then you go this way. 3 times x is 3x, and 3 times -1 is -3. You clean up the like terms inside. -x plus 3x is 2x, and then you open this bracket. So you get 2x squared plus 2x minus 3, and that's the answer to part B, the equation in standard form. C, use a graphing calculator and a quadratic regression to verify the accuracy. You know what you can do is you can even change the points on a whim. What I mean by that is if you just, how do I do this? If you change your points here, okay, the curve is gonna change in real time. That's why Excel is a little bit better than Desmos. So now if you see, I put this as -4. You see the curve changes. You see that? It changes in real time. -3, -2, -1, 0, 1, 2. So those are all my x values. Now I'm gonna plug all the y values. 10, 0, -6, -8, -6, 0, and 10. So that's all the points plotted. And did we get the same equation? Slightly different, okay? Negative 2x squared, 4x minus 6. We got 2x. Actually, no, we got the same thing. I made a mistake opening the brackets. 2 times x squared, 2x squared. 2 times 2x, 4x, 2 times -3 minus 6. There we go. So we got the exact same answer. It's because these points are very nice. They go through the x-intercepts. There's a nice vertex. All of them are whole numbers. So if you do it by hand or if you use technology, you're going to get the same thing. You're going to get very different results or significantly different results if you use, I don't know why this is lagging. If you were to graph this, you see this one? these points are not nice. If you do it by hand, if you use technology, there's gonna be some significant differences. Not gonna bother with this one, but the idea is the same. You plot it, see if it goes through the x-intercepts, find a vertex, find the a value, find the b value. Question for you here. Look at our data points. If I asked you, is this model valid? This could be a question. What's the y value? Okay, what's the y value when the x value is 3? Is this model valid to answer this question?
It's not.
Why? Because the model uses x values from -4 to 2, yeah? We do
Mm-hmm.
not know what the model looks like beyond this range. That's why we don't know if the model is valid for points beyond 2 or -4. Like over here, at 3, it might come down. You see it like that?
Uh-huh.
But if you use this model, you would say it's like 12 or something, but turns out it's actually 6. It's because you don't know this, so do not make predictions beyond the range. It's more of the same, right? Anything different here? Um, Nothing is too different. We're gonna do number 11, but first, let me ask you. So let's say that these are the points that you get, okay? These are the points that you get. What's a good model here? A linear model, which looks like this, or a quadratic model, which looks like this. Which one's better?
A linear one.
Why? It depends on how well it fits, yeah? The quadratic, for it to
Mm-hmm.
be quadratic, like it needs to drop down, and we have no indication of anything dropping down. So quadratic is not valid here, okay? How can you check that though? I'm gonna show you how to check that using technology. Very easy check. What you need to do is find something called, let me select the data. You need to find something called the R squared value, okay? Go down here, R squared, see that? If the R squared value is high, okay? If the R squared value is high, that means it's a good fit. Look at this. For the quadratic, I'm just gonna pull this in. R squared is a measurement of how well the model fits the data. This is our quadratic model. R squared is exactly 1, yeah? That means it's a perfect fit. This is not going to happen in real life. R squared is going to be somewhere between 0 and 1. 1 means it's a perfect fit. Not really, doesn't really happen in real life, but it does because these points are very nice. Now, for the same data points, if you were to use a linear model, okay, let's go linear. Now look at that. What happens with a linear model? The R squared drops to almost like 0.3, 0.3191. That's using a linear model. Is because we know this data point, these data points, they follow a parabola, right? There's a nice U-turn. Linear model, small r squared, quadratic, a perfect r squared, quadratic is the way to go, okay? So that's how you can use the r squared value to see which one is valid. And there's more to it than just the r squared value, but r squared is a good starting point. But it's also kind of deceiving though, like, and this is called bad data. Like you can have something like, vehicles on the road on the y-axis, just some random variable, vehicles on the road, and you can have colors of monkfish in Lake, I don't know, Ontario or something. Look at these two variables. They have nothing in common, yeah?
Mm-hmm.
The colors are not influenced by the vehicles on the road, let's say in like New York or something, or some random city. So these variables, they have nothing in common. But if you were to plot them out, right? And let's say you get, these are the data points, yeah? And you add a linear model to this, and turns out your R squared value is nice. Let's say it's like 0.92. Does that make any sense? It does not, okay? So this is just a coincidence that this is a nice R squared value. These two variables have nothing in common. You cannot use this model to predict the vehicles on the road in New York based on the colors of monkfish. Even though there's a high R squared value, yeah, if you make a prediction, it's gonna be junk. It's not gonna make any sense. So this can be deceiving at times. Even if it's our nice R squared value, you can get variables that have nothing to do with each other. So do not make predictions using this model because your model was flawed to begin with, okay? You cannot plot these two and expect a good result. So that's something we can talk about later in regression, but the X and Y variables, they need to have something in common. That's gonna be the step one that you do before you even collect data. Okay, the X and Y variables, they need to have something in common, or they need to be dependent upon each other. Let's go back to this one. Now this is pattern finding. Imagine this square dot pattern, okay? Let's say X is the diagram, and Y is the number of dots. The first one has 4. The next one has 16, I believe. The next one has 36. How many dots are there in the 20th diagram? Justify your answer. So find the pattern is what this is. Do you see a pattern between the X and Y's? Let's see what Excel spits out, and then I'll tell you how to do this. So again, a new sheet, you can use the same sheet, it doesn't matter. So diagram 1, 2, 3, we had 4, 16, and 36. Let's do this. Insert charts, and a linear would work here, okay? A linear would work, but because we're doing quadratics, we're gonna stick with polynomial degree 2, any of the equation, 4x squared. So that's what it spits out, okay? So that you can see that's already the answer to that question, 4x squared. The 3e minus 13, this thing, what does this mean? You see this 3e minus 14? E means 10 to the power of, okay? So what that means is 3 times 10 to the power of negative 14, which means you have, again, negative exponent means there's going to be a bunch of zeros. You have 0.00014 zeros, okay, 14 zeros, and then you have this 3 at the end. So this number is very, very small. You can ignore it, okay? Look at how small it is. It's not even like 0.03. It's like 0 point, and then there's 14 zeros, and then there's a 3 at the end. So this number here is insignificant, okay? So you can ignore it if you would like. That's what that means. But how would you do this by hand? Now, I'm looking at the patterns here. We know these are perfect squares, right? 4, 16, and 36. What squared is 4? Something squared is 4. What's the number?
2.
2. So that 4 is 2 squared. 16 is 4 squared. 36 is 6 squared. You see the pattern? The next one is going to be 8 squared. Okay? You're adding 2, and you're squaring them. The next one will be 8 squared. Okay? So 1, 2, 3, 4. And as you can imagine, the next one will be 10 squared. So that's the fifth one. We need to go all the way to 20, right? So what's the next one going to be? After 10 squared.
12 squared. 12
12
squared.
squared, yeah, exactly. Now what's the pattern? What's the equation here? For 1, you have 2 squared. For 2, you have 4 squared. For 3, you have 6 squared. So y, yeah, is going to be something squared. Does that work? X plus 2. Um, 2 plus 2x. No, it's just 2x squared. 2x squared. That works, right? When x is 1, you get 4. When x is 2, you get 16. Yeah, there you go. That's the equation. 2x squared, okay? 2x squared. You take this number, you multiply that by 2, and then you square it. That's the pattern. So that means the 20th one, we know if you keep going here, the x value will be 20 here. What's our pattern? You take this number, you multiply that by 2, and you square it. So we have 40 squared, which is 40 times 40, right? That's 1600. So there you go. On the 20th diagram, there's going to be 1600 dots. Does that make sense?
Mhm.
So that's a pattern finding question. Okay, you just need to find a relationship between all the x and the y values. Can get very, very tricky. This one wasn't that bad because we know it's a quadratic, so we know something's squared. But later on, you'll see that it's not always gonna be that easy. What's the pattern here? So again, we have x and y. We have figure 1, 2, 3. The first one has 3. Second one has, what is this? 6, 8. The third one has 12 plus 3, 17. What do you think the pattern is? Let's see what it tells us. Okay, this can be tricky, right? But I can already tell it's gonna be this number, yeah? You're gonna add this number. Your y is gonna be something in this form. Because here we added 1 on top, here we
Isn't
add,
3 15?
it's 15. Oh, you're right, actually, it's 15, yeah, not 17. 4 times 3 plus 3, it's 15. Any ideas about a pattern? Don't worry about it. Let's see what it spits out. You can just change this, right? I told you this. You can just change it, and it's gonna change it in real time. So 1 was 3, 2 was 8, 3 was 15. And there you go. The pattern is x squared plus 2x. Does that make sense? X squared plus 2x. You take this number, you square it, and then you add 2 times that number. 2 squared plus, yeah, it works. 9 squared plus 6. Yeah. So what's the question actually asking us? Determine an equation for this relationship. Done. Um, what about this one? What restriction must be placed on x to model this relationship? Remember, x is the figure number. Can x be anything? Can x be -5? Remember, x is the
No.
figure number, so there you go. X cannot be negative, okay? Cannot be negative. What else? Can it be 1.5?
No.
No, it cannot. It has to be a whole number, right? It has to be a whole number. So how can you write that? You can just write it in words. If you want to write it mathematically, x has to be bigger than or 1, and x has to be an integer. Integer means it's a whole number, okay? So that's how you denote it. Greater than equal to 1 means 1, 2, 3, 4, 5, 6. Well, it can be 1.5. This thing means you can be 1.5, but then this thing means it has to be a whole number. So that means 1, 2, 3, 4, 5. And that's the answer to that question. And here's this communication question. Can the factored form always be used to model a curve of good fit that appears to be quadratic? What do you think? Yes or no? Can you always use the quadratic? The factored form? What do you need to use the factored form? You need a key information.
The x-intercepts.
The x-intercepts. Does a quadratic always have x-intercepts? Does it need to have x-intercepts? No, it doesn't. Look at this. You can get something like this, which is never going to go through the x-axis. So let's say that's negative x squared plus 2. Or you can have something like this up here. You see that? That's never going to pass through the x-axis. These graphs up here, they do not have x-intercepts. That means you cannot write them in factored form, okay? So can a factored form of a quadratic? No, the answer is no, because not every single quadratic has a factored form or x-intercepts. If you get a model, if you get your data points like this, right? Let's say like that. Can you do this in factored form?
No.
No, right? Because those are your data points. If you fit a curve, it's going to look something like this. And that thing doesn't have x-intercepts. What about we flip this question? What if I asked you, can the vertex form? What about now? Yes or no? Can you always use the vertex form to model a quadratic relationship?
Yes.
Yes, you can, because every single quadratic must have a vertex. It doesn't need to have an x-intercept, but it must have a vertex. Let's do this one. What's going on here? All right, so again, the first one is easy. There's 1 in the first one. How many cubes are there in the second one? I'm gonna say 7. Do you agree? There's 1, 2, 3, and
Mm-hmm.
then there's fourth one, and then 5, 6, 7. There's 7 in the second one. The third one, 9 on the bottom, yeah, and then 8 on the top. I'm gonna write this as 4 plus 3, just to find the pattern. This one we have 9 on the bottom and 8 on the top, which is 17. What's the pattern? Okay, would this help if I wrote 1 as 1 squared plus no, 1 is not very useful to find the pattern. We need to find something with 4 and 3. The way I'm thinking about this, look at this. And again, this is very tricky, right? These are the trickiest type of questions. You see this number here doubled, yeah? Or it got squared. It got squared, and then you're adding 1 less than the squared. You see that? For 2, we squared it, and then you're adding 1 less than the squared. Same thing with the 3. We squared it, got the 9, and then we're adding 8, which is 1 less than the squared. So that's our pattern. Y is going to be x squared, yeah, plus x squared minus 1. So the fourth one will have 16, we'll have 15, we'll have 32. Cool? That's something you need to, these are like terms, you can even collect them. So this is going to be x squared plus x squared, this can be 2x squared minus 1. So that's our equation. Let's see if Excel spits that one out as well. 1717. It should, right? It should. 1717. Yeah, we got the same thing because these are very nice points, right? Again, you see the 3e minus 14 thing? It always does this, but you can completely ignore that because that's a very, very small number. It's like 0.14 zeros and then a 3. And completely ignore this. And then we get the same answer. So that's the answer to part A, okay? Oh, no, actually, no. Part A, we just need to plug 15 in there. Number of cubes, 15th model, it's going to be 2 times 15 squared minus 1. 225 is 15 squared times 2, 450 minus 1. 449 is the answer to part A. Part B, which model in this pattern would you build using 1249 cubes? How do we do part B? Do you plug x as 1249 or y as 1249?
You plug Y.
You plug y. Okay, help me solve this. 2x squared minus 1. So this was our equation. 1249 is equals to 2x squared minus 1, right? 1249 it was. Yeah. How do you solve this quadratic equation for 1? Oh, sorry, for x. What am I saying? What do you do first?
You add 1.
Yeah, you add 1. You get 1250. What's next?
You divide by 2.
Yes. What's next?
You square root.
Yes, you square root. Usually when you square root, you get plus and minus. Remember that the square root of 625 is plus 25 or minus 25. But we're talking about figure numbers. Minus 25 makes no sense. So x has to be 25. So the 25th figure will have 1249 cubes, okay? And again, the restrictions here on the x is the same. X has to be 1 or more. It has to be 1 or more, and it has to be a whole number. You cannot have decimals. And those are the restrictions for x. Whole number just means this. Look at this, the way I write it. X is an element of integers, and integers means the whole numbers. Integers can be negative, but we've placed a restriction on x that it's positive. So that's the restriction. And that's it for today.
Okay, thank you.
See ya.